Okay, while our next speaker gets set up, I will go ahead and introduce him. This is Bharath Sankaran. He got his PhD at USC with Stephen Shaw, and after that founded Scaled Robotics in Barcelona, Spain. Yeah. And he does some really interesting work in construction sites, and I won't go into details. I won't spoil it for you. I'll let him do that, but it's very related to a talk we did earlier in the day. So I'm very excited for this.
Yeah. All right. There we go. Yeah. Awesome. Okay. Can you guys hear me? I think you just push the button. Oh, doesn't not work. This one. Yep. It went off. Try again. Right, it's on.
Well,
hit it one more time. Do you mind if I reach? Yeah, go for it. Go for it. Try it.
Hello.
There we go. Whoa, it works. It's going to be a tough act to follow Melanie, absolute legend. So I'll try my best. Since 99% of you outside of Mac and maybe Connor don't know who I am, I'm going to introduce the work we do, why we do it, and why it matters. And then kind of get into the nuances of the challenges of how academia is just orthogonally, the incentives are orthogonally aligned with where industry actually needs it. So I work in construction, and come on now. That work? Wonderful. So first introduce the problem of what we're trying to solve in construction, how we think about it. What are the practical challenges we face, and how none of this is aligned with where academic research sits today. And then possible areas of how to think about these problems, like how do you take solutions, how do you engineer them to the construction site. So first of all, why is robotics interesting in construction? I'm not sure most of you guys know, it's one of the world's largest industries, 30 trillion worldwide. But it's also one of the world's most wasteful and inefficient, to the extent where a typical construction site, 30% of it goes into a landfill. So they generate an incredible amount of waste. Not just that, why is it right for innovation? The average construction project has a 0 to 2% margin, which means on average they're at loss. They don't make any money. So any innovation is going to help them. But if you think about construction, it's basically manufacturing. It's on-site manufacturing. And other manufacturing sectors are hitting 50% margins versus construction is struggling. So what caused this disparity? And our view at Scale Robotics is traditional manufacturing, shop house, in-house manufacturing, established very efficient process control. And construction lacks process control. So we think about the way of improving construction margins, efficiency, reducing waste, is just basically doing better process control. Quick controller diagram to see how you relate the idea, and then I'll jump into where technology can come in. So your reference state is something called a BIM. For those of you who are not familiar, it's a 3D model that evolves over time. So it's a 4D model of how the construction site needs to look. Obviously, on a construction site, the controller is the people working on the site, and the system is the physical construction process. How do you go ahead and know what to measure to figure out what to optimize? Our internal view is the end objective of construction is to recreate a 3D model in space. So measure the 3D model. And this should be a very good proxy to inform you about how the process is evolving. Because if the model is wrong, what you've measured on site is wrong, then clearly the process is wrong. The way you can internalize this analogy is another complex process that we tend to trivialize most often. It's cooking. Cooking is a complex biochemical process, but there's a lot of heat exchange, chemical processes, thermodynamics. But the best way to measure if your process is going right is to understand the objective of cooking. What is the objective of cooking? To make something taste the way it's supposed to taste. So taste it when you cook. If it tastes bad, something is wrong with the process. Pretty much the same analogy. So there are opportunities for AI and robotics here. Basically two. One is, how do I capture the state? And the other one is, what do I do with it? And this is where you'll see two universes and divergence between what industry cares and what academia does. Academia, I would say, is very focused on this bit. And our robot is also in there, so I'm not taking a specific dig at anyone. And we built 500,000 solutions for how to capture data. What industry really cares about is what do you do with that data. It's not about getting from point A to point B. Because what ends up happening when you end up focusing on one of the problems and not thinking about the whole greater problem is the incentive set and the value proposition is not clear. A lot of contrived, problem sets, forcing solutions to fit problems rather than working the other way around. Classic product development is you ask your clients what they want, and then you work your way backwards to build the technology that needs to solve that problem. Rather than, here's my tool, please use it with whatever comes across your way. And this is a line I want to use. Why robotics adoption in general has been very, very bad in the industry outside of very controlled sectors like manufacturing. Why we haven't done a great job is, I'm just going to paraphrase something Wolfram said, I guess, in ICRA when I was a young graduate student. It was like almost a decade back. Your solution either has to be better than humans, or cheaper than humans, or both. It cannot be neither. You can't be more expensive and crappier. That does not work. And to give you a sense of why this is the problem academia tends to commonly run into is probably seeing lots of papers of, oh, we're doing X in construction, Y in construction. This is where, probably step before. This is the real problems you run across when you practically take solutions into this industry, especially in construction. First of all, there's no static world and there's no static reference signal. A construction project is constantly evolving. So basically your reference signal is constantly evolving. Second problem is it's highly nonlinear if you get on a construction site. There is no relationship to what's happening on one side of the site to another side of the site. In fact, we have an internal joke at Scale Robotics that the only thing linear about construction is gravitational causality. You can't build floor 4 before floor 2, everything else flies. Then the other problem is it's an extremely dynamic environment with workers, materials, scaffolding, people moving around, all kinds of issues that play into your sensing. And none of the algorithms that have been built today actually take that level of complexity into account. And finally, this is a problem very unique to the construction domain, is it's a decentralized problem. If you walk into a construction site, try this the next time, go ask one person, what are you doing today? Or what are you building? And go and ask another person. They'll have 2 or probably different answers because every team maintains its own plan. So it's a decentralized process control problem where the reference state is evolving and it's extremely noisy. And to add on to all of this, another problem that does not occur in shop floor logistics and manufacturing is it's also an open system. Your construction site is neither indoors nor outdoors. It's neither day nor night. So I can keep adding these analogies and you'll see where all this noise comes in. So this is where you should be starting with thinking about a problem because that affects how you implement solutions. There are environmental challenges. I said this at a workshop earlier. There are all these 6 million object detectors that are there. In practical industry applications, no one cares about cats or bottles that you can classify or dogs or whatever it is. The real challenges are lighting variations, low frequency and high frequency noise, things that are modeled, things that are unmodeled. These deter your perception abilities on a site, on an industry application, especially something like construction. Then there are practical limitations of effects of unreliable time. How do you get from, since the environment is evolving and it's dynamic and there are these issues, it's not just, oh, can I take a path like this? And these things have to be, like Melanie was mentioning, repeatable and reliable because your clients are planning around what your robot is going to do. So if that is not reliable, then the rest of it is not going to be useful at all. Also, another big issue is we say, oh, there's some uncertainty in the state estimation, and hence I'm just going to leave that as a confidence metric. It does not work because your client doesn't care about your uncertainty. They will kill your product. They say like, okay, your solution is not reliable. I can't trust you, so please leave, and we'll try to find the next solution. And here's the biggest thing. Academia, your mistakes, you can put them in a nice little PR curve and then show that I tuned my precision, I tuned my recall. Worst case, your paper doesn't get into CPR, NIPS, ICRA, RSS, whatever it is. Here, costs of mistakes are exponential, right? From someone losing millions of dollars to unfortunately, loss of life could also be in it. You have to be extremely careful. And these all add into your implications. These are all the implications when you have to think about capturing data rather than can this get on the most complex terrain. Then another aspect is about analyzing the data. There's a huge wave for DL and DL this system and DL that system and end-to-end learning. Anyone who employs a DevOps engineer knows they hate DL models in production simply because no one wants to get a call at midnight and they don't know what to fix on a production system. Most DevOps guys will be like, give me a lookup table. I work with that because I know it's predictable, it's reliable, and I know what to do when it breaks. A million parameters, and then you tweak one outer distribution event, boom, the whole thing explodes. It's not something people care about. And why do the systems need to be built to that? Because it affects machine learning. Unfortunately, in the real world, you don't have properly labeled data. The first time we encountered the data is when we figure out what the labels are for it. Every event is an outer distribution event when you're out there on the field. I mentioned earlier, it's extremely noisy, the data is sparse, it's never complete, and it's sometimes just incredibly hard to discern the signal from the noise. So what does all of this look like in reality? So I'm just not complaining, we actually have a solution, but you'd be surprised how engineered it is for us to work. So this is the only video I'll probably bore you guys with. Let me see if I can play this. Yeah. This is about a typical construction site where people want automated solutions to be deployed. These are the kinds of sites we go on. Here, it's impossible to figure out what is building and what is not building. And this is where we are able to deploy our solutions for quality control. And I would want to, like, the rest of the talk kind of walk you through what are all the things we do to make it happen, which is not aligned with academic consent. Here, what you're seeing is our algorithms automatically go in, filter out all the high frequency and low frequency noise from the scan structure, which, by the way, is not scanned with SLAM. The SLAM is unreliable and not particularly useful. And then we go ahead and do machine learning on it. Again, there's no one size that fits all. Models that exist, anyone who does any level of machine learning on production-based systems will tell you, you ensemble everything. It's a hierarchical model because nothing can break in production. You always need a fail switch that you can trigger. So let me move on. So what are the problems that, at least from our perspective, we see? One is, first of all, solving the wrong problem. Trivializing the settings, non-heuristic, problem settings, brittle parameter settings. Let's start with solving the wrong problem. Everyone and their uncle is focused on object detection. Most of our problems, or majority of the domains we work in, object detection is not the issue. No one cares if the object is there or not. What they care about is what state is the object in, because that is what defines their process. So, but we don't solve, state of cat. Is this cat in progress or is this cat not in progress? That's not what we solve. It's like, oh, I can find cats, I can find dogs, I can find this. What they really care about is what is the state of the object. Second thing is trivialized settings. I went and I dug on Kaggle to find the most up-to-date construction data set that I could find. You're like, oh, this is so complex. Actually, it's not. So well-centered, well-illuminated. Here is one of our simplest data sets. I'm not even throwing the hard ones on it. It's just 6 captures of the same wall. And this is what kind of information they care about. So it's just a wall at different stages of construction with really bad lighting. There's no geometry consistency. And for all the image-based detection and all those folks, everything's great. So you're not going to work with the texture and get a lot of flexibility out of it. So these are issues that they don't focus on. Then there is the non-realistic problem settings. They're like, oh, it worked on this, my robot flew to this. It's a common one I've seen. Oh, I have a construction site, I'm going to fly a drone and scan it. This is when people have really not spoken to anyone in construction. It's not legal to fly a drone inside a construction site. That should have been the first point to stop that line of research and then say, let me do something different. Second thing, here it seems like, yes, maybe my robot could walk through this. No, simply because that's wet concrete. There is rebar, there is water over there, they're moving machinery, someone is there, there's a safety barrier. I don't think there's any platform we built that can go through this, but this is where they need these solutions to work. Not the ones that we deliver on a regular basis through our papers. Or a more simple solution where it's like, in this environment, we have the model, we have everything to navigate. But what the robot sees is pretty much this, because the rest is covered in snow. There's no information coming out, and mostly it's dimly lit, so the camera is also utterly pointless, and you have to get this. So I've given you, a lot of problems, and then the last one is, very, I guess, ML, DL, all those focus, actually mostly DL focus, is brittle parameter settings. You throw a model and, you tweak one little thing and it breaks. What industry expects is for things to be reliable and explainable. Whatever happens, they cannot break in production. And where do these algorithms fall apart? Here, it's impossible to say what the semantic meaning of any of this is. It's even hard for a human. But if you ask a more engineered system, it will tell you why it came to decision X or Y, or at least limit you and say where the confidence margins are. Current algorithms, especially DL algorithms, are confidently wrong, and you constantly get in trouble with your clients, and hence don't work. So then, is this the end of the world? It's not. I'm here to give you more positive. What are the possible directions? We strongly believe autonomy is not key. Literally, no one in the industry working on asset classes of 20, 30, $40 million all the way up cares about your autonomy. They want it to be reliable, accurate, and precise. That is all the problem. Second thing, systems don't fail gracefully. Most of the robotic systems that we build, it's either it works or the whole world has come up, fallen apart. They have to fail gracefully. They have to fail in an explainable way. Everything cannot be learned from data. This is a new trend I've been hearing at conferences, and sometimes what annoys me is you could be sitting on an incredible amount of data. Like for us, every month we bring in somewhere close to 6 or 7 terabytes of data. It's not enough. Every news project we get on is an outer distribution. We've never seen anything like that before. It's an industry-specific problem, a sector-specific problem, but it's also a general problem as your data sets don't generalize that well. ImageNet is not the world, literally, trust me. And you have to go into a little bit of a history, understand that a lot of the things that were built in image-based recognition, etc., was built on content-based image retrieval. For things to work on mobile apps, which is not working with the world, you are interacting with the application passively. That's very different from a robot, which is actively interacting with the world. So, like I mentioned, we have proof is in the pudding. Every construction site we've gone on to, the people over there have just been like, drive the damn thing around. There are also liability issues and everything else, which is who's paying for the insurance if you let it run by yourself. It's a totally closed, contained environment. That's fine, but the construction site not so much. When I say fail gracefully, is things have to be explainable. You throw one DL model code, ask it to just run the entire way. I've used neural networks as a illustration. We don't rely on them. Algorithms have to fail gracefully, and to the point of learning from data, you can collect as much information as you want about a wall. Nothing about this in any amount of data you collect is going to tell you that this is a wall under construction. This is actually a lot of domain expertise. So a second takeaway, another takeaway over here would be, don't try to solve general purpose problems. In fact, I want to make that a key takeaway, which is, I know we like to call ourselves scientists, and I'm not sure I'm very comfortable with that term. We are engineers, and our job as engineers is to make things work. And making things work means the thing has a utility or a purpose. So check with the person who is going to serve about what you're trying to solve, and work backwards from there and try to make it work, and just try to build one general Swiss Army knife that doesn't really work anywhere else. And this goes to the same point. So, what are the big takeaways? In the kind of robotics applied to construction, there are the two aspects I spoke about: capturing data and processing the data. Always remember, any insight is better than no insight. Probably another takeaway that I like to use, which people might debate me on, is there's this whole thing that robotics and AI is meant to replace labor. I don't like to think of it as replacing labor. I think of it as enhancing, basically force multipliers. There are a lot of tasks that cannot be accomplished today just because of the complexity or fatigue or lack of skilled labor. And instead of trying to replace it, which is a much, much harder task because you have to go full autonomy, try to just be a force multiplier to make sure you can do it time 10x, 100x, 200x, 1000x, because that has more value. Because any client would be super happy with you remote teleoperating, operating to whatever it is, as long as it works in all of the problems. in all of their settings. Rather than it worked once, it works on the site, it doesn't work anymore. The second thing is going back to the processing data. This is, again, how you think about problems. I got this from a guy who worked on Google search, one of the early developers and engineers over there, and said something very interesting, kind of stuck in my mind. And I always wonder why, as roboticists, we don't think that way. Google search doesn't give you the right answer. It gives you the most relevant answer to your query. So the user is somehow forced to provide the right constraints, and then it works. We should also think about robotics, automation, kind of in the same way. Here is my environment. I need this planner to work here. I don't care if it works in another parallel domain, blah, blah. I need it to work here. What about the environment can I use and use as constraints to solve this optimization problem rather than just general purpose trying to throw, the kitchen sink at it. And with that, I'd like to wrap up and just thank my team. And this is a point I wanted to make specifically because a lot of people tend to forget. It's also probably important for robotics is we built a nice little diverse team. Where we have 50% gender balanced, we have equal representation. Why is this important? Diversity in people is diversity in thought. And a common mistake we tend to make as roboticists is when we address a problem, we get other roboticists to sit in and discuss amongst ourselves rather than you're building a solution for someone else. Construction, bring the civil engineer into the room, bring the architect into the room, bring the BIM VDC manager, bring all of them into the room and then find out their problem and you provide the solution. If you just keep talking to other roboticists, you're probably not going to build the right solution. That's all I have to say.
Okay, do we have any questions for Bharath? You can use the mic here in the room. I can kick us off. I had something I noticed when you were talking, Melanie's talk. You both kind of poo-poo probabilistic robotics. And as a student of an author of the book Probabilistic Robotics, that hits a little close to home.
I know.
So my question for you, and we can ask Melanie as well during the panel talk, does probabilistic robotics have any place in industry at all, anywhere?
I would say this, right? It's a wonderful book. I've also read it. I have one in my library, and I encouraged all the junior engineers they come in so that it just develops their mathematical skill. If it's not quantifiable and it's not reliable, then that probability estimate means nothing. So your uncertainty should be actionable. The problem is we throw out uncertainties that mean nothing and are not actionable. Like if I tell, okay, go to a client and you say, oh, this algorithm works 85% of the time. So it's like, okay, so what is the 15% it fails? It's like, I told you 85% of the time. And then push you again. When does it fail? And that is not useful. So if it's quantifiable, it's relatable, then you can build a product around. In fact, you can deliver a solution with it. And ultimately, that is our objective as roboticists, to build things that work. So we should always tie that in, saying that, okay, there's an uncertainty estimate. If it's just a blind uncertainty estimate, it's utterly useless. And then places where, here's the thing. Oh, this algorithm performs 96% where blah, blah, blah. It is not the best case performance that industry cares about. It's the worst case performance. Your worst case performance should not be awful, should not be the end of the world. Best case is fine because ultimately your problems come from the worst case performance. So building a foundation on that where you have to say that this is a fail-safe system. It can do this, like she was saying, 100% of the time the algorithm just works. And that's it. Like, oh, SLAM has to work this way. Stick markers. No one ever said don't stick markers. They want it to work. We stick markers everywhere on terrestrial laser scanners to get them. This is not even mobile platforms because the end application is the map has to be within a few millimeters accurate. So yes, we stick markers and a lot of things, you have to make it reliable. Any other questions?
Can you elaborate a little bit more on fail gracefully, in particular how that relates to autonomy? Many of the people here are really focused on autonomy.
Fail gracefully is either, this is the thing, right? Like, I think this ties into probabilistic robotics and all of those things. When I mean by fail gracefully is if my confidence in this result is below a margin, instead of just exploding on the face of the planet, I want something more useful to happen. Either the system stops, queries an expert human, but they should not be catastrophic failures. And as much as you want to have end-to-end systems, they all lead to catastrophic failures. The most reasonable way to prevent these things is to have very strong state machines. It's probably what most people put in is just say, all right, if this happens and you're not able to produce something, just jump and don't embarrass me and make me lose my X, zeros contract and leave it as is. So this is what we mean by fail gracefully, is you should really care about when the system fails, how it fails, try to categorize that, or find a way to push the system to do something that is safety critical and safe and reasonable, not just drop off. Yes.
You had a small comment in there about teleoperation.
Yes.
Do you use that in your fleet? And if so, like, what's the breakdown between teleoperation and
If I were to be realistic, Arun invited me for this talk a long time back. The realistic application for us right now is we've shelved all the robots there because it is incredibly hard to take them onto a construction site where they can have that. There are particular applications where we've used robotics. They teleoperate when we go there because the last thing we want is to be embarrassed in front of a client. And they want something useful to happen. So, if you start thinking about all these layers of autonomy that are there, you're driving a robot to capture. Here's another thing. All of SLAM was built to avoid things, not to map things. If you want to reconstruct an environment, you should see where the algorithms, what are the genesis of these algorithms, why they were first developed. If you want to reconstruct, just use good old structure for motion, multi-view geometry, and try to produce something as robust as possible. They're trying to do SLAM and produce a map that neither works for this nor works for that. So in those situations, like when we have to build those things, it's all teleoperation intuition. If I want to capture more data at a corner of a column, this is very hard to programmatically write in, but the site engineer knows that. And why you can't program it in is because the site engineer doesn't know that he needs that the previous day or week back. They look at the site and they're like, yeah, I need that. So let me just drive it and get it.
Okay, let's thank our speaker a second time.